up, we've got Howard, who was meant to be doing strobing, but no longer. And he's talking about quantum, what do we say now? Quantum effects. Quantum phenomena.
Alright, hi. Tonight I'd like to talk to you all about h-bar. Now, h-bar is one of the fundamental constants of our universe, and its value is 1 in 10,000 million. Does that look right? Someone count those. Okay, now that's a pretty small number, and you can think of h-bar as being the constant that determines how quantum, how weird our universe is. So what would it be like if h-bar was much bigger? If instead of being this mess of zeros, it was just 1? Well, the short answer is everything would get a lot stranger. So tonight, I'm going to try and give you some insight into quantum physics by talking about 3 ways that your life would be different if h-bar had a big value. Okay? So, the first thing is uncertainty. Now, I'm sure a lot of you have heard of Heisenberg's uncertainty principle. Our uncertainty in the position of a particle multiplied by our uncertainty in its momentum is always greater than or equal to some constant. Okay? Now, that constant depends on h-bar. So, if h-bar was much bigger, this principle would start to apply to us. Now, as an example to illustrate that, say you're driving along in your car, and you glance down at your sat-nav, and suddenly, your speedometer isn't working anymore. So you glance back at your speedometer, and now your sat-nav's broken. So, well, I bet we'll be closer together. But now they both go fuzzy when you try and look at them both at once. And you can't ever get past this amount of uncertainty. Another way in which your life would change is trouble with observing things. Now, at the quantum level, observing a system has a drastic effect on it. It's possible to freeze a particle in place by continuously observing its position by the quantum zero effect. So this would be like, say you're walking down the street and you see a friend and you stop to greet him. You stop observing each other and you can't move an inch until some convenient obstruction steps in and allows you to both go cautiously back on your way. This is in fact the way the weeping angels of Doctoral Training. Yeah, I thought there'd be enough people to get that. Okay, so the last thing I want to talk about is tunneling. So, it's quite common in quantum physics for objects to move through one another. But at our scale, the probability of that happening are minuscule. But, as you probably guessed, they depend heavily on h-bar. So if h-bar was much, much larger, you'd find tunneling occurring during everyday activities. You'd be walking through doors by accident, you'd get in your bed at night and you'd wake up under it. Cash would fall out of bank vaults and prisoners would slip out of jail. No one would buy any Apple products because your hand would go straight through them. And finally, and perhaps most importantly, the sun would become unstable and engulf the earth and all would spontaneously detonate. So, however strange and confusing you may find your everyday life, hopefully I've convinced you that the quantum world is even more bizarre, and you can be thankful you don't have to think about it as often as us or physicists.
You can see there's a theme probably that I should have of death and destruction. It's always nice to end a talk on a nuclear explosion. But next up we have Mark, who's going to be talking about time reversal symmetry. So can we have a large round of applause for Mark?
Thanks, Simon. Hi, everyone. So, as you've heard, I'm supposed to tell you about time reversal. Actually, I don't really know that much about it. So, instead I've brought along some friends of mine who do. And hopefully with this little experiment I've got set up here, we can meet some. So it's a bit fiddly, so excuse me while I set it up. But all I'm doing is just shining a bright laser. You can actually do this yourself with just a laser pen. And I'm going to shine it through a small droplet of seawater. And that'll give us, hopefully, just a little glimpse into a whole world of tiny little things floating around in the smallest droplet of liquid. And actually, so this laser microscope itself is one of the oddities of science. But that's not why I've shown it to you. What amazes me about this picture is the fact that these tiny little creatures can move around at all. Because Because you see, they're so minuscule that the relative friction forces on them are massive, which means that for them to just swim through water would feel like trying to swim through a thick, syrupy goo. So how do they do it? Well, I know what I would do if I found myself stuck in some syrupy goo. I hope that never happens. I'd be kicking my legs frantically to try and escape, to try and swim out. But unfortunately, that wouldn't work. And in order to understand why, we need to understand a concept called symmetry. So physicists love symmetry, but what is it? Well, when we talk about symmetry, we just mean something you can do that leaves things looking the same as they did before. And there's all kinds of these symmetries. The one I want to tell you about is called time reversal, which perhaps sounds a bit mysterious, but really it isn't. I just mean by time reversal, so if I say something obeys time reversal symmetry, I mean if I took a video of it and then played that video in reverse, it would look the same. So let me give you an example. Suppose I'm a bacterium, I'm going to try and swim along. Perhaps that's not too hard to imagine. Anyway, I'm going to try and swim by sort of waving an appendage around like this, back and forth. Now let's analyse that motion. Well, if I stop it and run it in reverse, you can see it looks exactly the same as it did before. So we say that this motion is reciprocal because it obeys time reversal symmetry. It's the same both ways. Now let me give you a counterexample. Motion in a circle, that breaks time reversal symmetry because if you stop it and run it in reverse, well, it's clearly going the other way. So you can distinguish the two cases. And that distinction actually turns out to be really quite important if you're a bacterium. Because as a microorganism trying to swim, what you really want to do is break time reversal symmetry. I mean, imagine a bacterium swimming along in some direction and then playing that in reverse. What's going to happen? Well, obviously it's going to go backwards. So swimming, by its very nature, must break time reversal symmetry. And that's why this kind of motion will not work. And it's such a simple argument, I find it almost surprising that it works. But in nature, we actually find that bacteria always use a motion which breaks the time reversal symmetry. And in particular, many of them do something a bit like this sort of circular thing. What they have is flagella, which are long spiral-shaped filaments which spin around just like a propeller. And it's actually the direction of that spin that determines which way the bacteria will go. So hopefully that seems fairly intuitive and reasonable. But I don't want to make things too easy for you, so I'll leave you with a little puzzle to think about. Given what I've said, which I've hopefully proved to you, that bacteria cannot use reciprocal motion to swim, what about fish? I mean, we all know that fish spend their whole lives doing reciprocal motion like this. So how can they swim? Well, unfortunately I'm out of time. So I'm going to have to leave it there. But if any of you are interested, then please feel free to come and talk to me after the show. Thank you.
Obviously these days it's quite hard to think that actually, by that count, using your legs would be very difficult. But at one point actually, and I'll leave the thought with you, you would have had your own flagellum motors yourselves, and you can try and work out